Hello and welcome to the first proper presentation on credit risk, where I'm going to be talking about GLMs, generalised linear models. Now, although this is a presentation on credit risk and GLMs for credit risk, it's worth bearing in mind that GLMs can be used for a whole load of other purposes apart from credit risk. I mean, anything where what you're trying to model is something which has a category as the dependent variable rather than a continuous variable, then GLMs are going to be useful. So if you're modeling credit risk where you're looking at something which might default or might not default, then GLMs are an obvious tool. But also if you're looking at mortality risk where you might have some people who either survive or don't, or you're looking at non-life insurance risk where there's an insurance claim or there isn't, GLMs are just as useful for that type of analysis as well. And also not just two categories. I mean, you can find versions of GLMs which can deal with a number of different categories, although those kind of go beyond the scope of what we're looking at here in terms of credit risk. So we're going to be sticking to the more straightforward ones here. So anyway, modelling credit risk and generalised linear models, GLMs. As it says, GLMs are generalised linear models, which is a type of regression which has its category, which has a category as its dependent variable. So this is typically a 0 or a 1, but as I mentioned, you can have more than one level within that. But in any case, what you need to do is employ some tweaks relative to what a typical regression looks like. So it's probably worth recapping on what a typical regression does look like and how regressions work. So if you look at the most standard linear regression, you've got a variable ym on the vertical axis and a variable xm on the horizontal axis, and you're trying to describe the linear relationship between them. So you do this by having a constant, which is b0, and a slope variable b1, which you multiply by xm to get you the line xm. Now, to get from the line to the actual dots, you have an error term, em. So whereas ym equals b0 plus b1 xm tells you what the line looks like, if you add on the em, that tells you the error term, the distance between the line and the points that you're looking at. So what this means is that if you want to find the best line to define this relationship between xm and ym, one way of doing it is to concentrate on these error terms and try to make sure that the sum of those squared errors is as small as possible. So why do you square the errors? Well, if you've got a squared error, it's always positive. So minimizing the sum of those positive numbers gives you the smallest overall distance between the line and those points. So if you rearrange that equation to get em is equal to ym minus b0 minus b1 xm, that gives you the error term in terms of everything else, and then just square them, sum them, and then you've got the metric that you need to minimize. And that's why it's called ordinary least squares estimation, because it's the ordinary version of this, and what you're doing is least squares estimation, minimizing those squared errors. And it's easy to extend this to more variables, but the principle is just the same. So if you've got n variables for m, say companies, your equation becomes ym equals b0 plus b1x1m all the way up to bn xnm plus that error term, which is what you want to minimize. So fitting ordinary least squares is actually straightforward. I mean, it's straightforward at least in as much as there is a closed form solution to it. So it involves calculus and it's not the most fun in the world, but you can get to an exact answer for what the parameters should be. So if you define a vector capital B as all of those little b's, b0, b1, all the way to bn, and you define a matrix capital X as xnm for all of those n variables and m firms, and you define a vector y as ym for all those m firms, then for ordinary least squares, b hat, which is the estimate of b, the estimator of b, is equal to the inverse of x transpose x multiplied by x transpose y, which, as these things go, is actually pretty straightforward. Finding it is a little tricky, but it is doable. And the key point here is that it is a closed form solution. So you're not tending towards something; you are finding the exact answer for those parameters in that vector capital B. Now, if you're doing ordinary least squares, and this applies to any regression really, you've got a number of assumptions that you need for the results to be valid. So the first is the data matrix has to have a full column rank. What this means is that you can't have any column which is a linear combination of any other columns that you're looking at. So if one variable that you're considering is equal to the second and third variable added together, or the fourth minus the fifth, or even just equal to the sixth, then OLS doesn't work. And the reason it doesn't work is when you've got these kind of relationships, trying to find the inverse of the matrix X, it doesn't work. So you need to have full column rank. You need to make sure the independent variables aren't correlated with the error terms. If they are, then it means you've got some misspecification. The error terms shouldn't be correlated with each other. So if you've got error terms correlated with each other, what this means is that what's happening in one period is affecting what's happening in subsequent periods. So you've got serial correlation or autocorrelation, and you need to start dealing with it with adding lagged variables and things like that. The error terms should have a constant finite variance, so it's got to be a finite variance, otherwise you can't minimize the error terms. And it needs to be constant, because if you've got a variance in your error terms which, say, increases over time, then when you're minimizing your sum of squared errors, that minimization is going to be focused on where the errors are the biggest. So you need to do something to deal with that if you do have what's known as heteroskedasticity. And also you need to have a linear relationship between the explanatory variables and the dependent variables, which sometimes means you need to do a little bit of tweaking. So as I say, most of these do have fixes. For full column rank, just check the data. Look at the correlations between the variables for a start. I mean, that's a good indication. If you've got a very high correlation between any of the columns, then you might not have full column rank. If you haven't got a constant variance for all the error terms, then you might want to weight the error terms in your regression, and you get towards things like weighted least squares and generalized least squares. Explanatory and dependent variables having a linear relationship. If they don't, then you need to think about applying some sort of transform to your explanatory variables. So either taking the log of them, raising them to a power, inverting them, something which gives you something which looks a bit more like a straight line, which you can then apply the regression analysis to. Now, that being said, a linear relationship is impossible in some cases. So, for example, if your dependent variable takes a value of 0 or 1, you're going to have a lot of trouble getting a linear relationship between the stuff explaining that dependent variable and the dependent variable itself. And if you are looking at credit modeling, well, that's what you're faced with. You've got explanatory variables which can take any value in theory. So you're looking at things like, say, balance sheet items, asset values, profitability, and so on. But your default either happens, in which case you assign a 1, or it doesn't, in which case you assign a 0. Now, the way that you deal with this is you have a link function. So the right-hand side of the equation stays the same. It's still a bunch of explanatory variables which are weighted by the coefficients that you use. But when you get to the sum of that, you apply transform so that the result falls between 0 and 1. And this gives you a generalized linear model. Now, for credit modelling, there's a couple of popular types, which are the Logit and the probit model. So the Logit model, you start with the same linear equation as before, but instead of having your dependent variable as ym, it becomes ym star. So ym star is equal to beta naught plus beta 1, x1m, and so on and so forth, plus the error term. But of course we are interested in ym, which can take a value of only 0 or 1, because a firm either defaults or it doesn't. So the way that we deal with this in a Logit model is what we look at is the probability that ym is equal to 1 given the matrix xm, and we define that as the exponential of y star m over 1 plus the exponential of y star m. So when we're looking at this expression here, if you think about what happens when e to the y star m is very small. When it's very small, you get something which tends towards 0. When e to the y star m gets very large, it tends to e to the y star m over e to the y star m, which is 1. So you've got a function there which is always going to be between 0 and 1. And this essentially represents the probability of default that you're seeing with the parameters that you've found to apply to the variables that you've got. And as I mentioned, xm is the explanatory variable vector for firm n. Now the probit model is very similar. You start with y star m, or ym star, ym star, y star m, one of the two. But here the link function comes directly from the normal distribution. So mathematically we write this as the probability that ym is equal to 1 given xm is equal to capital phi of y star m. So essentially you're taking a value there for y star m which can take any value at all, and then you just apply the cumulative normal distribution function to it, and that clearly gives you a number which is bound between 0 and 1. So what you're trying to do here is you're trying to make sure that your parameters b0, b1, b2 all the way to bn are such that you've got a model where if ym is 1, then either the logit of y star m is close to 1, or the cumulative normal distribution function for y star m is close to 1. And if ym is equal to 0, then the corresponding function is close to 0. So you're trying to maximize the likelihood that the link function of this expression here is as close to 1 or 0 for defaulting and non-defaulting firms as possible. So this brings us to fitting Logit and probit models, which isn't as simple as for ordinary least squares because there's generally no closed form solution for this. So the approach uses something called maximum likelihood estimation, and trying to solve for maximum likelihood uses numerical methods. Or you just do everything in a statistical program such as R, in which case the answer is very straightforward indeed. But it's worth showing that you can do it in Excel, just because you can see exactly what's happening in R. And it takes a little bit of work, but I think it's a helpful example to show exactly what's going on. So fitting GLMs in Excel, it's possible, they're not ideal. I quite like doing stuff in Excel because you can show how things work, and you can also check your understanding of how things work. And what's also quite nice is if you do something in Excel and then you do it in R as well, and you get the same results, which I'm happy to state is the case here when I did this in Excel and in R as well. So anyway, what you first need to do is define your likelihood function. You then log it and sum it, then use the solver to maximize your likelihood function, and that gives you your parameters. So I'm going to use the Logit model here as the example. The probit model is very similar, and I'll run through each of these in a sequence so you can see what's going on. So the Logit model in Excel, remember what we've got is this expression y star m is equal to b0 plus b1x1m plus all the way up to bnxnm and the error term. And the probability that ym is equal to 1 given xm, so that vector for firm m, is equal to e to the y star m over 1 plus e to the y star m. So the first thing I'm going to do is just shorten that probability expression to the probability of ym, and we'll just take it to mean the probability that ym is equal to 1 given xm. And the reason for that is, the slides are only so big and I don't want to take up more space than is necessary. So how do we get from this to the likelihood function? First, just a bit about what the likelihood function is. The likelihood function is essentially saying what is the probability of each of these dependent variables having the values that we have assigned to it. And then the probability of all of the dependent variables having that likelihood is everything multiplied together, because the probability of the first firm having that likelihood multiplied by the probability of the second firm, and so on. So that gives us, for the likelihood function, this product here across all of the different firms for m is equal to 1 to capital M of this expression. So the first bit, probability that ym is equal to 1 raised to the power of ym. So if ym is equal to 1, that means it's defaulted, and we want the probability default. And that's what we've got. PR of ym raised to the power of 1. What that means is, if the firm has defaulted, the second part of this expression is just equal to 1, because that 1 minus PRYM to the power of 1 minus ym is going to be raised to the power of 0. It's going to be raised to the power of 1 minus 1. So it becomes irrelevant. If you've got a firm which hasn't defaulted, so ym is equal to 0, conversely the first part of this expression is equal to 1 and becomes irrelevant. And the second part, which is 1 minus the probability that ym is equal to 1, in other words, the probability that it hasn't defaulted, is raised to the power of 1 minus 0, which is 1. So essentially, if you've got a firm which has defaulted, you've got the first part of this equation, PR of ym. If the firm hasn't defaulted, you've got the second half of this equation, 1 minus PR of ym. And you've got them all multiplied together to get to the likelihood function. Now, the next thing we do is to take logs. Now, there's two parts to this. The first is, why can we take logs? We can take logs because if you're maximizing a likelihood function, the parameters that give you the biggest value for the likelihood function will also give you the biggest values for the log of the likelihood function. Because the logarithmic transform is what's called a monotonic transform. Essentially, if L1 is higher than L2, then log of L1 is higher than log of L2. And because we're looking at probabilities, we've got positive values all the time, so you can take logs. So that's what we do. At least that's why we can do what we do. Why should we take logs? Well, maximizing a sum is much easier than maximizing a product. And if you take the logs of one thing multiplied by another thing, so all these probabilities multiplied together, if you take the logs of those, instead you get the sum of a whole load of series. So what you get is the sum of ym log of the probability plus 1 minus ym log of the probability. And again, this is going to be something which gives you the log of the probability of ym if something's defaulted, and the log of 1 minus the probability of ym for something that hasn't defaulted. Then we need to find the values of b0, b1, all the way to bn, and to do this we need to maximize log of L. So you could, if you wanted, write an algorithm, but because I'm not a complete masochist, I choose to just use the solver which is built into Excel, which is pretty straightforward to use. So this is what the data looks like that we're using. So the first column here is labelled default. If it's 0, the firm didn't default. If it's 1, the firm did default. We then got EBIT over assets. So earnings before interest and tax divided by assets. Now, EBIT can be positive or negative. Assets is always positive. So this gives you something which is going to be reasonably symmetrical. Don't think we need to do any transform on that. The next one, we're looking at assets divided by liabilities. Now this one definitely isn't going to be symmetrical. It's only going to be positive. It's probably going to have quite a lot of right-hand skew. So to transform it into something which is more likely to have a linear relationship with, well, with whatever you're looking at normally, I take the log of assets over liabilities. The next one is retained earnings over assets, again can be positive or negative, and finally free cash flow over assets, again can be positive or negative. Don't really feel I need to apply a transform to this. Now I should say I haven't looked at this, how skewed any of these data items are in any great detail. I haven't selected them with any great insights. I've just picked a bunch of variables which could, in theory, give some insights into whether a company defaults or not, and left it at that, because I'm not trying to build a model that I can actually use in practice. I'm just trying to demonstrate how these things work. And this is how it does work. This is what the Logit model looks like in Excel. So running through the various components of this, you'll see we've got the cells highlighted blue here. These are the parameters. And the cells highlighted red, these are the variables that we apply those parameters to. So in cell H6, we've got the sum product of B2 to F2 times B6 to F6. And you can see I've fixed the blue cells at row 2, which means if I copy this formula all the way down, it's always going to be the product of the parameters in blue and whatever row I'm looking at. You also see I've added an extra column here, which is column B, which is always 1, and that's essentially just to multiply the constant by, so that in any for any firm that I'm looking at, I've got that constant of, in this case, 0.573530 added to whatever else I get, and that sum product, that is y star m. The next cell is in I6, which is the Logit function. So it's e to the h6 over 1 plus e to the h6. So that is simply calculating the Logit function, the link function, based on y star m. And then in J6, I've got the likelihood function for each individual firm, which you can see is A6 multiplied by the log of that probability plus 1 minus A6 multiplied by the log of 1 minus that probability. And I do that for every single firm, and then I sum them to have the full log likelihood function. So then the next thing to do is to actually try to maximize this. And to do this, I need to use Solver. So if you're using Solver in Excel, the first thing you've got to do is make sure it's enabled. So you go to the Options menu item, and you go to Add-in. Then you click on the bottom Go at the bottom, and you make sure that the Solver add-in is enabled. Then when you've done that, you go to Data and Solve, and you put in the appropriate cell. So what we're trying to do here is we're trying to maximize cell J1. So you'll see that button there we've ticked as max. You'll see the set objective is set to J1. And we want to maximize it by changing the cells in B2 to F2. The only thing we need to do is to make sure that the cell saying make unconstrained variables non-negative is unchecked, because we don't care if they're negative or positive. And then there's no other constraints that we need here, so then we just click on Solve, and that gives us the answer that you see there for those parameters B0 to B4. Now the sensible approach is to use a statistical program such as R. It's free, it's particularly powerful for matrix operations, so if you can do anything in terms of vectors or matrices when you're using R, it'll work far more quickly, because it's not so good at processing loops, so try to avoid loops and use matrices if you can. There's a large community involved with R which creates specialist packages for things as obscure as you could possibly imagine. I mean, I used one once for calculating robust standard errors for a Logit regression on an unbalanced panel, which is pretty niche, but someone had thought of it and had written an appropriate package that I could use. You can download it at this web address here from the R project, and I tend to run it through a program called RStudio, which I just find it handy for being able to see what's going on, being able to edit files directly. It just makes it a little bit more usable. And if you're just using RStudio for yourself rather than for a group of people, RStudio is free as well, so it's definitely worth a look. So when you're running R code, it's helpful to put the code into a file first so you can run it time and time again rather than just typing everything repeatedly into the command line. And you don't really want to do that if you can possibly help it. The first thing that you'll want to do though when you're using R is to load any libraries. So the first few lines are usually loading the libraries you're going to use in the rest of your code. And to do this, you may need to make sure those libraries are actually available, which means that you need to install them as packages. So for this, in RStudio, at least you just go to Tools, Install Packages, and make sure that you've got everything installed that you need. It's also important to set the working directory in R, which doesn't just tell you where the file's going to be saved, but it also makes it easier to import data, because if you've got the working directory with all your files in, then you don't need to type in long directory addresses to be able to tell R where it should find the stuff you've got to use. So for now, in terms of packages we need, the only special package is one called XLSX, which is useful because it lets you import data from spreadsheets. For any particular functions which use special packages later on, I'll install those as we need them. But for now, you just need to put library brackets XLSX into the file which has your code, highlight it and press Ctrl Enter. That runs the selection. I'm going to use the same data that I used in Excel. The workbook name that I had was Credit Example XLSX. The data were on the second worksheet. The sheet name doesn't matter, it's just knowing where it is, and it's the second one. And I put the workbook in the working directory, so we're all set. Then you just need to run this code here. What it does is it imports the second sheet from the named workbook and puts it into something called a data frame. And the data frame is called data file. Then the second line just displays the data file. So if you see it here, got library XLSX, then some code. Anything you put after a hash sign in the file doesn't get processed, it's just a comment to make sure you can remember why you've done what you've done. And then, as you see, it reads in the data file and shows it. And then the bottom right window shows what you actually see. You can see I set the working directory to the appropriate place. It loads the library, then reads in the data, and then displays the data file, which reassuringly is the same as the Excel data that we initially loaded. Then if you want to run a Logit model, you simply type this code. So again, you want to put the results of your model into something, so we call it Logit result. The function we use for a GLM is called GLM. And you then need to type in this fairly typical string of code to run any kind of regression in R. So the dependent variable is called default, which is, as you remember, the first column we had. And that is explained by the variables EBIT over assets, log of assets over liabilities, retained earnings over assets, plus free cash flows over assets. So that's the expression that you use. It's a GLM, and you're telling it it is a binomial family of GLM, and the particular type is one which is linked by the Logit function. And then the final thing is, well, you've come up with all these names: default, EBIT over assets, log of assets over liabilities. Where do they come from? Well, the data is in a data frame called data file. So you set data equals to data file, and then you type Logit result, and that gives you the results of that GLM. And it's very similar code for probit results. You just change the link from Logit to probit. Then if you run this code, these two lines, this is essentially what you get. You get the coefficients, and you get a few high-level results from the analysis. including the Akaike information criterion, which tells you how good a fit it is based on the number of variables that you've used. And indeed, if you want to rewind to an earlier point in the video, you'll see the coefficients here are the same as the one that I got in Excel. So fits measured by the AIC, which is, as you remember, a calculation based on the number of variables n and the log likelihood. So it's 2 times n minus 2 times log likelihood. So lower is better. Fewer variables is better. So, whilst your likelihood will improve as you add more variables, there's a penalty for this because it increases n, so that increases the AIC, which is a bad thing. Now I can get additional information on the results of the GLM by using the summary function. So summary brackets Logit result gives additional information, and it shows that everything isn't great. What we want to have here as the results of the regression is like loads of stars showing huge amounts of significance, and we've got 1. So log of assets over liabilities is significant at the 5% level. Nothing else is significant even within the 15% level. So it's not great. Now, why could this be? One simple check is just to look at the correlations between the explanatory variables. And what you can see from here is that EBIT over assets and free cash flow over assets are highly correlated, plus 80%. So that's going to mess with the fit and mean that your fit isn't as good as it could otherwise be. So you might want a simple check might just be to remove one of these variables from the regression. So free cash flows over assets appears the least significant. Let's pull that one out, and if we do this, we find that we get greater significance and we get a lower AIC. So just showing the summary, you can see that now you've got 2 variables significant at the 5% level, and you've also got an AIC which is only 37, it was 39. That's a slight improvement. So this is just very high level and a very simple way of looking at it. But you can see how simple it is to make these minor changes to the regression and look at the results. So that's everything for GLMs for this session. Hopefully that's given you some insights into how you can use generalized linear models to model credit risk, but also to model anything where you've got a yes/no answer. So as I said, insurance, general or life insurance, can both benefit from this type of analysis. And hopefully what this also shows is that both that it's easy to run this stuff in R, it's very straightforward to get results in R, but also it's not too hard to do it in Excel. And if you do it in Excel, even though you don't get all the additional summary statistics, you at least get an idea of what's going on in this analysis and what R is doing when it's carrying out the maximum likelihood estimation. So that's everything for now. Hopefully that was useful. Please do leave me any comments if anything wasn't clear. I can't promise I'll answer, but I'll try. And feel free to subscribe to the YouTube channel if you want to make sure you're kept aware of the next in this series, which I will record shortly. Thank you very much.